Welcome to Chapter 5, Part 5. Now we're going to talk about our last sort of category of stereoisomers. So when we go through isomers, this is a nice sort of flow chart. Isomers, just anything that has the same formula but is different, is a different compound. Constitutional isomers have different connectivity. They're kind of the most obvious to see. Stereoisomers, same connectivity, but different arrangement in space, right? You can't superimpose them on each other. If they are non-superimposable, but they are mirror image compounds, they fall into enantiomers. If they are stereoisomers, but they are not mirror images, then they fall into a category of diastereomers. So we've actually already talked about one type of diastereomer. For instance, the the trans-2-butene and the cis-2-butene. These have different arrangements in space. They are not mirror images of each other. So this falls into the category of diastereomers. And that was on the next slide. I'm glad I drew it. Diastereomers have different physical properties, right? These aren't chiral compounds we're looking at here, so they're not going to have optical activity, but they are going to have different melting points and boiling points and different physical properties that we can measure. They may be close, they may be similar, but they are going to have different physical properties, unlike enantiomers, which are going to have the same physical properties and just that difference in optical activity and chiral molecule interaction. But there are other types of diastereomers, and before we jump to that one, let's look at another possibility. Let's get a fresh page here. What about if we have two chiral centers? So let's say we have a chlorine and a bromine on this ring. Well, we know that there are going to be a few different options, right? For one, the chlorine and the bromine could be cis to one another. Now, the carbon that has the two halogens, those are both chiral centers, right? There's a chlorine coming towards you, a hydrogen going away from you. If you go around the ring this way, you get to a carbon with a bromine first. If you go around this way, it's a CH2, right? So it's four different groups. So there are two chiral centers here. You can draw the enantiomer by reflecting that through a mirror, or you could change the wedges and dashes. There's just different ways to do it. Right? These two are enantiomers of one another. But we also have the trans option, right? The trans cyclohexane, where the bromine and the chlorine are on opposite sides of the ring. There's still two chiral centers, so we can draw an enantiomer by reflecting or switching up wedges and dashes. So these two are also enantiomers. But all four of them are stereoisomers. So if we think about what the relationship is between these two, or these two, or the cross relationships here, these are going to be diastereomer relationships. So there can only be a set of two enantiomers, right? That's like your twins. But you could also have, like, say this is a family. There are two sets of twins. Now, 1 and 2 are twins, but 1 and 3 are siblings, right? 1 and 4 are siblings. 3 and 4 are twins, right? 3 and 4 are enantiomers, 1 and 2 are enantiomers, but every other combination would fall into the category of diastereomers. The number of chiral centers you have increases the possible number of stereoisomers. So what you'll notice is two chiral centers, right? Two stereo centers. leads to 4 isomers here, right? 4 stereoisomers. And that is something that we see increase as you get more and more. When we look at this 6-membered ring with an OH, a methyl, and a chlorine on it, there are 3 chiral centers, and so we wind up with 8 possibilities. So, let's see, these are all in the green boxes, your sets of enantiomers, but then the relationship, right, between compounds in different boxes, right, lots of different combinations we could look at, those would all be diastereomer compounds. They're all connected the same, right? They're just arranged differently in space. And so if they're not mirror images of each other, they fall into the category of diastereomer. Now, the number of possible diastereomers or stereoisomers that you could have comes from a pretty easy, here we go, formula. The maximum number of stereoisomers is 2n. No, that's wrong. Hold on. Fix this. You're in your notes. You're taking notes right now. Something we want to correct. It's not 2n. That must be a formatting issue. It's 2 raised to the n. N is the number of chiral centers in the compound, right? So 2 chiral centers, 2 squared is 4. Here, where you have 3 chiral centers, 2 cubed is 8. All right, so you can look at the number of chiral centers and you can figure out how many possible stereoisomers max there could be. So we can look at a larger molecule like cholesterol and we can figure out how many stereoisomers there are by counting the number of chiral centers. So let's go into highlight mode. We have 1, 2, 3, 4, 5, 6, 7, 8 chiral centers here. Now, none of the CH2s are chiral centers. This guy down here is not a chiral center because there's 2 methyl groups. So you can pause this and do the work for yourself, but there are 8 chiral centers. So how many possible stereoisomers could there be? Well, that's going to be 2 raised to the 8th, and I got my calculator out because I don't know that off the top of my head. Let's see. Sorry, y'all get to, this is exactly what we'd be doing in class, so, bear with me here. 2 raised to the 8 is 256, right? So 256 possible stereoisomers. Hopefully that gives you a little perspective on how difficult it could be to synthesize something like cholesterol. As organic chemists, what we're going to start to learn about is manipulating functional groups, building larger carbon-based molecules, and you can do it. You can build 6-membered rings. You can build bicyclic structures. You can add alcohols. You can put in double bonds. This is all challenging enough. But now you add in the fact that there are 8 chiral centers, and if you don't get the stereochemistry around each one of them correct, you could wind up with one of 255 other stereoisomers. Then you can start to understand how difficult synthesizing these larger, more interesting biomolecules can truly be. Now, there is a reason we keep saying maximum number of stereoisomers. There is not always going to be the maximum number. So we are going to introduce the idea of the Miso compound. All right, the Miso compound is when you have and I'm sure it is defined on another slide, but we're going to define it here. A Miso compound is a compound with chiral centers, so those carbons with 4 different groups, but the compound itself is achiral. So you might be thinking, well, how could that be? Well, let's take a look at 1,2-dimethylcyclohexane. That's what they have drawn here. We know that there could be trans 1,2-dimethylcyclohexane. And as it turns out, that's not really even specific enough because there are 2 trans 1,2-dimethylcyclohexanes. So to be really accurate in naming, if you have wedges and dashes now, you can assign R and S. But that's a little bit beside the point here. These are enantiomers, right? You cannot flip one around to get to the other. Feel free to pause, take a minute, build a molecule, and verify that for yourself. These are 2 different molecules. If I take this one and I rotate it, then the wedged carbon here is going to be on the bottom. If I take it and I try to flip it over sort of horizontally, then this wedge will become dash and the dash one will be on top. There is no way to make left superimpose onto right. So perfect definition of an enantiomer. However, let's look at the diastereomer of the cis 1,2-dimethylcyclohexane. That's definitely a diastereomer of the ones drawn above it. It's an isomer, different arrangement in space, not a mirror image. But let's look at what happens when we reflect this one through a mirror. Sorry, it was kind of messy here. These are mirror images, but they are superimposable. If I take this one and just rotate it, it becomes the one on the left. This is known as a Miso compound. They are identical. It is a compound that has chiral centers. These carbons are both chiral centers. They are carbons with 4 different groups. But because there is a very specific plane of symmetry, we don't wind up getting a chiral molecule. So for one, cis 1,2-dimethylcyclohexane is achiral. It has no optical activity. There is no enantiomer. And when we think about this compound here with its 2 chiral centers, it does not have 4 stereoisomers. It only has 3 stereoisomers because you get the 2 trans isomers and then the meso cis compound, right? And it has to do with this internal plane. When you have that high degree of symmetry, you wind up with meso possibilities. Because those 2 CH3s are the same, that is why this happens. That's why we didn't see this when we had chlorine and bromine, right? You can't rotate this one around. They'll both be wedged, but the chlorine will be in the wrong spot. But when we have that high degree of symmetry right here, we wind up getting a meso compound. Now, you can certainly test this experimentally with optical activity, but you can also just look for planes of symmetry. That is the type of molecule I'll be asking you about. There are more complicated ways to get meso compounds with rotational symmetry like this one. I don't want you to worry about this. Let's not highlight it. Let's say you don't have to worry about inversion and reflection points. The main thing I'll be interested in is that you can recognize meso compounds when they have a very clear line of symmetry in them. Okay, so overall, a compound that has a plane of symmetry winds up being achiral. That is how we wind up with these meso compounds. Now, identifying meso compounds, here's a few other ones. Just to give us a little practice, we have a line of symmetry here. We have a line of symmetry here. We have a line of symmetry here, right? It doesn't have to be a ring. And so when you have those lines of symmetry, you are going to have less than the 2 in formula. The last thing that we are going to talk about are Fischer projections. So we'll just continue on here so this can be a final chapter 5 lecture video. We've looked at a lot of different ways to represent molecules, represent them in 3D with chairs, with wedges, with dashes, with Newman projections, and Fischer projections are another important one. Fischer projections come up a lot in biochem when you get into sugars. And it's sometimes called, so there's the Fischer projection, sometimes known as the bow tie projection. And that is because what you are going to see, and it's defined here, horizontal lines are coming towards you. They are wedges. So horizontal lines make a little bow tie. Right? And so that always helps me remember. Vertical lines represent the dashes going back into the page. Now, a lot of times when we draw tetrahedral carbons, we do 2 in the plane, a wedge, and a dash. And that's really useful. But Fischer projections are really nice when you have a bunch of chiral centers in a row, like you have in sugars. So you can determine R and S from a Fischer projection because we do have that 3-dimensional information. So if we were looking at something like this, let's go ahead and determine if this is R or S. You have hydrogen, you have OH. I'm going to go ahead and write what this is. CH3, CH2, CH3. So we're going to assign our priorities. Oxygen is 1, hydrogen is 4. Carbon attached to carbon and 2 hydrogens is 2. Carbon attached to 3 hydrogens is 3. You can attach 1, 2, 3. Now, what's nice about Fischer projections, you don't ever have to do double replacement because 4 is always either in the back or in the front. So since the 4th priority is coming towards you, we're gonna do the opposite of the rule. So if clockwise is R, in this case, it's going to be S because 4 is wedged, right? So you don't ever have to do double replacement. But you do have to be careful. You cannot draw this any other way. You can't rotate it. You can't flip it around because what is implied by the Fischer projection is what is horizontal is wedged, what is vertical is dashed. So you have to draw them consistently. You can't just turn them around. Fischer projections, most useful when drawing these molecules with multiple chiral centers. All of these are representations of different sugars. You have pentoses and hexoses here. You see that the chiral centers kind of stand out where you get these crossed lines. You could identify the configuration R or S on each one of those green dots, right? And I definitely recommend practicing. You'll have to in your homework. There will be extra practice up online. It also helps in identifying relationships. It can be pretty easy to identify enantiomers, right? These mirror images. It's easy to recognize diastereomers, like this all connected the same, but clearly the bromines are not mirroring each other here. It can even be helpful in determining Meso compounds. So there's no Meso compounds here because R1 and R2 are different. But if you had the same R group on the top as you do on the bottom, right, then you would be able to see that line of symmetry really easily. And so you'd be able to determine, hopefully quickly, right? That's the idea. That's why we use different projections to communicate. You would recognize that this has a Meso relationship. These are identical. I could take this one and rotate it and it would be exactly the same. There is a practice set up on eCampus of determining the relationship between 2 molecules. And that is going to be a definite part of your test. It's going to be part of your quiz next week. I give you 2 molecules and I ask, are they identical? Are they constitutional isomers? Are they enantiomers? Are they diastereomers? Miso is also identical. So sometimes it's written Miso, sometimes it's written identical. Is it just 2 different structures altogether? And so that may feel like, I don't know how you're feeling at the end of this lecture, it may feel like a big task, in which case you should do a lot of practice before you get graded on it. It may seem like, oh, I got this and I don't need to practice, in which case you definitely should practice. That is where we can really hurt ourselves in organic and get behind, is when we get a little too cocky. This requires practice, and so I will provide you with plenty of it. Make sure you take the time early to do it, as we will continue to move on. I'm just going to go through these last sections rather quickly. When we think about conformations, this is not the same as isomers. Conformers are different arrangements in space that one molecule can make because it has kinetic energy, right? This is an image of butane. And I could also draw butane like this, right? But because we have free rotation around that single bond, these are not different molecules. These are just different conformations. And so we're not worried about, we don't use sort of Newman projections to show stereoisomers. We use them to show conformers. The same thing happens with chair conformations. We don't tend to talk about isomers using chair conformations because it's hard to see the plane of symmetry. So while yes, 1,2-dimethyl cyclohexane definitely would be adopting a chair conformation to ease that angle strain. It is hard to identify the isomer relationship when you're thinking about it in terms of chairs. So if you come to a practice problem with chairs, go ahead and draw it flat. And you'll be able to tell, for instance, if you have a Miso compound. The reason that it doesn't matter that this doesn't have that plane of symmetry when it's drawn in the chair is because it can go back and forth, right? It's going to be an average of those conformations. So we can determine isomer relationships and if Miso compounds are possible by just looking at the flat sort of aerial projection or the Hayworth projection. I have a few practice problems that ask about relationships using chairs, and that's my recommendation. Draw them flat. If both of these are going up, well, okay, now both of these are going up. So now I see there's an internal plane there. That's going to be a Miso compound. We won't worry about atrope isomers, but it is kind of fun to think about and to be aware of their existence. There are chiral compounds that don't have chiral centers, and they tend to be these larger molecules that get, quote unquote, stuck in a position. So BiNAP, in theory, can rotate around this single bond right here, right? It's a single bond. There should be free rotation. But PPH2 is phosphorus with 2 benzene rings on it. So you have these 2 enormous groups right here. So when you try to rotate, they knock into each other. And so it prevents it from rotating. And so you actually get 2 optically active stereoisomers just because this big bulky interaction keeps it from rotating. Again, I'm not going to ask you about these, but you can start to see that the world of stereochemistry can get much more complex, which is just let you in on a little secret, always true, right? Everything you learn can get more and more interesting and complex. Allenes are another functional group that exhibit optical activity and chirality, even though they don't have chiral centers. I will not be asking you about allenes either. Let's see, how many more slides? Oh, okay. The last topic that I will talk about, I do want you to know these terms. When it comes to enantiomers, because their physical properties are the same, it can be very hard to separate them. And as we've discussed, it can also be very important that we can separate them. Think about naproxen, right? One enantiomer is therapeutic, one is harmful. And so we have to be creative when it comes to separation of these type of molecules. Distillation would require them to have different boiling points. Recrystallization would require different solubilities. Enantiomers don't have those differences, so we can't use that. So there are 2 ways. There are 2 ways to resolve or separate enantiomers. And it's essentially, the Pasteur method doesn't work for most things. So Most of them are going to utilize a resolving agent where essentially you are reacting them with something to make them not enantiomers anymore. So for instance, here's a pair of enantiomers react with this other chiral molecule. I forget the name of it, but it creates these two diastereomers. Now, diastereomers have different properties and can be separated. So once you make them into diastereomers, now what you can do is separate them, right? And then, so you have one diastereomer and another diastereomer, and then you can reverse the reaction, right? So you can go ahead and make it not the salt again so that you can get, and I don't know what the reaction is that would allow you to do that, but there is one. That's why they choose this particular compound, is because it's reversible. And then you can get these separate. So they can be a little challenging to separate. Maybe you went out of your way to make this compound. It's taken all this time. And now just to clean it up, you have to do another 2 reactions. So that's resolving enantiomers using a resolving agent. Another way to clean them up is chromatography. So we are going to talk about chromatography some this semester in lab. We're not going to do chiral chromatography because that's a little bit more complex. But chromatography uses 2 phases. There is solid phase, there is liquid chromatography, there is gas chromatography. But what you do is you have a stationary phase, right? So something that is going to be stationary. That is usually solid. And then you are going to have a mobile phase. So either a liquid or a gas carrier. And then your mixture will be carried over that stationary phase. And as it reacts with that stationary phase, different components of your mixture, let's say we have a mixture of A and B. A might move slower, B might move faster. And by the time they both leave that column or that chromatography paper, or this is even utilized in different gel separations in biology and biochem. By the time they move across that chromatograph, across through that experiment, one will come out first and the other will come out second. Think about, sometimes we do chromatography experiments with dye with little kids. You can use a coffee filter and you can place, right, so coffee filter, this is my rendition of a coffee filter. And right in the center, you can place a blob of ink. And as you allow alcohol to absorb into that paper, and the alcohol is going to go out in all directions, sometimes you start to get banding. So, for instance, if we use a black ink, a lot of times you will start to see that black ink is never just black. Maybe there's a blue band that comes out of it, and sometimes you'll see maybe like a purple band that'll come out of it, and I don't know. I haven't done this in a long time. I don't know if there's green, but you'll see that those different colors will interact with the paper and move slower or faster, and you can actually separate those different inks. Well, you can do that with a lot of different mixtures as long as your stationary phase interacts with the different components. And we do know that enantiomers not only have different optical activity, but they react with other chiral compounds differently. So instead of using paper like in a coffee filter, you can use a chiral stationary phase. And so your enantiomers will spend more or less time interacting with that chiral stationary phase, and you will be able to separate them. That is, if you work with a lot of enantiomers and you need to separate them, chiral chromatography is great, and it is a big time saver. Now, I am going to put this in chapter 7. chapter 7. We can come back to it, but I will put this exact slide in chapter 7 when we name alkenes. Just like, for instance, let's look at this compound. You could name this compound cis 1 bromo 2 chloro cyclohexane, but the more accurate name would be to use R and S. So just as a very last bit of practice here, bromine would be 1. This carbon down here would be 2, 3. Hydrogen to the back is 4. So in position 1, we have clockwise. So this is going to be 1R. It's clockwise. The fourth priority is to the back. 1R. Let's erase what I've done here. Do your best. There we go. If I do the other one, chlorine is 1, carbon with bromine is 2, carbon with hydrogen is and carbon is 3, and the hydrogen is 4. 1, 2, 3, going counterclockwise. H is to the back, so it's 2S. So the most appropriate way would be to name this 1R, 2S, 1 bromo, 2 chloro, cyclohexane. All right, now that you know how to determine RNS, you should use it in naming. It's more specific. Well, the same thing is true when we get to double bonds. Cis and trans is not always specific enough. We will cover that, though, in chapter 7, where we have a whole section on naming alkenes, so we will come back to that. You're welcome to look into it here, but I will have a video about it in a couple weeks. All right,